In this video, we're going to handle thread synchronization. We'll talk about critical section, entry section, exit section, and also rest condition with the help of the code. We're going to look at how can we handle thread synchronization if we do not use Mutexes, which stands for mutual exclusion. And if two threads without Mutex try to access the critical section they are in rest condition, the result of the shared resource will be abnormal. So I'm going to need some header files. So the first thing, and before that, remember, I'm going to write a code without mutexes and show you that the result will be abnormal, different each time we execute the code. And when I use mutexes, we will fix this solution. So I'm going to include the thread header file and also a library called chrono, right? And you must be using C++11 compiler. If you are using div C++, you can update, just Google it, how to switch to C++11 compiler in div C++, and for sure, it's going to give you the result. We need a shared resource because the synchronization problem happens when we have a single resource and more than one thread are trying to access that particular resource. So I'm going to declare a global counter variable. I'm going to change its value to 0. And then I'm going to create a function called increment, whose purpose in life is going to be to change the value of the counter and make it plus plus, but not just once. Let's do it a couple of times. For example, let's for 1000 times, right? So I'm going to execute this piece of code, counter plus plus 1000 times, so that we can clearly see the result. I'm going to move this code above. Okay, Control Z. That's it. And then we are going to put 5-millisecond delay. So I'm going to say thread, this underscore thread which is currently executing this piece of code. I'm going to say sleep for, and it's just a very simple line of code. The thread class has a sleep for method in which we just simply pass the chrono milliseconds method, which takes 5 milliseconds. So what this piece of line does, it seems very complicated, but it's super easy. Once you type it quite a few times, you will remember it by heart. It means that delay the next execution of the loop cycle for 5 milliseconds, right? And let me just reformat my code so that it looks nice. Yeah. And then I'm going to create two threads. And both of the threads will be executing this function simultaneously without the mutex. And I'm going to come here and say thread T1. So I'm creating an object of the thread class and I'm passing into the constructor of the thread class that function without the parentheses. Remember, do not put parentheses. It's a syntax error. So this T1 is going to call increment function and execute that function in a separate thread. Then I'm going to say T2. It's going to call it again, just like T1. And then I want to finish, stop finish these, wait for the execution of T1 and T2. Once they both finish their execution, I would display the value of the counter, that now the value of the counter is this, right? Save changes and recompile the code. It's going to take a little bit more time because 5 millisecond and 1000 time. So if you multiply 1000 with 5 millisecond, 5000 millisecond and 5000 milliseconds, it's going to take some time, maybe quite a few minutes. So let's run this code now. I'm going to just pause the recording for a few minutes and then we'll come back. And as you can see, the result is 1944, right? The reason for that is we were expecting the value to be 2000. If T1 is executing this line 1000 times, and each time it increments the value of counter, the value of counter should be 1000 from 0 to 1000 because 1000 times we are performing the same operation. And if T2 is also executing this line 1000 times, and each time it increments the value of counter, so 1000 plus 1000, 2000. So the result should have been 2000, but it's not. It's less than 2000. The reason for that is that counter plus plus is not an atomic operation at processor level. What it means is it is basically three-step operation or three instructions. And that is read the value of the counter. This is the first instruction. Then adding 1 to it. This is the second instruction. And then the resultant value should be stored back in this counter using this assignment operator. This is the third instruction. So when the CPU is assigned to T1, T1 comes and it executes, let's say, reading the value of counter and then adding 1 to it. But before it assigns the result back to counter, it was switched or the processor was assigned to T2, interleaving the operation, right? So this counter plus plus, this complete operation was incompletely executed. And similarly, it's going to happen quite a few times, so giving you inconsistent result. Now, very small fix, and that is including the mutex. And before that, I promised I'm going to teach you what is the critical section. So just before this particular line, counter, which is a shared variable, right? This is the critical section. The code is shared by both the threads. They're trying to access the same code. So it is called the critical section. And of course, counter is a variable which lives in a memory location. So you can also refer to the critical section is that part of the memory which is accessed by more than one thread simultaneously. So this is basically this particular code, this particular line is basically the critical section. And before this, above, it is the entry section. Entry section is just when you are about to enter the critical section. And once you finish execution this line, then we are in the exit section. Right. So this and the race condition is this phenomena that when more than one threads are in race to access this particular critical section. So this call is race condition. And to avoid race condition, we need mutexes. So I'm going to include the mutex header file, which is available in C++11. And all I have to do is to create a mutex object, mtx, let's call it mtx, good name. And then just after the entry section, we are going to put a lock, mtx.lock. So when the thread enters the critical section, before entering, it's going to put a lock so that other threads can only wait. And once it finishes execution of the critical section, it's going to release that lock. So I'm going to say mtx.unlock. The lock and unlock function works in the similar manner, like acquire a lock and then release a lock. So I'm going to compile it again. And I'm going to execute this piece of code. We're going to wait for a while, and when we come back, we'll see exactly 2000. And here it is. So each time you execute this code with mutexes, it will always give you the correct result. Mutex is used to control access of multiple threads to a single shared resource. What if there are limited number of resources and we have multiple threads trying to access those resources? How to control them? We're going to see that next.